Today we're covering pages 124, 125, and 126. So 3 pages to cover with today's video. You definitely want to have a calculator. Compound interest. Compounding is a process in which a savings account's earnings from interest are reinvested to generate additional earnings. Compound interest is paid on an initial investment, called the principal, and on previously earned interest. Interest earned is often expressed as an annual percent, but the interest is usually compounded more than once per year. So the exponential growth model, a equals lowercase a times 1 plus r to the t, is modified for compound interest problems. Given capital P, which is the amount initially invested, otherwise known as the principal, lowercase r represents the annual interest rate expressed as a decimal. Lowercase n represents the number of compounds per year. T, time, or number of years. The amount, capital A, in the account after T years is given by the formula A equals P times 1 plus R divided by N raised to the NT. So this is a formula that you need to memorize. It's not given to you on the formula sheet. You must memorize it. So write it off to the side. A equals P times 1 plus R divided by N, close parentheses, raised to the NT. Memorize that formula. Our first exercise, a person invests $500 in an account, so this is the initial investment, that's P, that earns a nominal yearly interest rate of 4%. This is our R. 4% as a decimal is 0.04. Remember, percent means hundreds, so you can always grab the calculator and take 4 divided by 100, and that will give us the decimal value. Calculate the amount of money in the account. There's a few words missing here. After 1 year, if the interest rate was compounded as follows. If it's compounded quarterly, that means the interest rate is happening, or it's compounded 4 times per year. So that is our N value. N equals 4. Write down the formula. A equals P times 1 plus R divided by N raised to the NT. The more you write it, that's going to help you memorize it. P is 500. R is our 0.04. N is 4. Go to the calculator. This is dollars and cents, so we'll round it to the nearest cent, which would be 30 cents. $520.30. If the interest is compounded monthly and is 12, A equals 500 times 1 plus 0.04 divided by 12 raised to the 12 times 1. Just going to take that, grab it, change the 4s to 12s. $520.37. Daily, there are 365 days in a year, so N is 365. Capital A equals 500 times 1 plus 0.04 divided by 365 raised to the 365 times 1. $520.40. So the higher the number of compounds per year, you see there's more of a slight increase in the amount of money in the account at the end of the year. Exercise 2, how much would $1,000 invested at a nominal 2% yearly rate, so P is 1,000, R is 0.02, compounded monthly, N equals 12, be worth in 20 years, T is 20. A equals P times 1 plus R divided by N raised to the NT. Now replace our variables with their amounts. And put it into the calculator. $1,491.33. Option 2. If $1,500 is invested 2.5% interest compounded weekly, how much will be in the account after 10 years? Weekly, N equals 52, R is 0.025, and P is 1,500. And time for A is 10 years. Capital A equals capital P times 1 plus R divided by N raised to the NT. And please, as you're working through these, you're also putting the values into the calculator like I am. You're not just watching me do that on the video. So nearest dollar, that's going to be $1,926. B, how many years will it take for the account to reach 2,500? Round to the nearest dollar. So 2,500 equals 1,500 times 1 plus 0.025 divided by 52 raised to the 52t. Okay, so we want to solve this for t. Well, t is part of an exponent, so we need to get this base and exponent by itself. So the first thing we'll do is divide by 1,500. This simply reduces to 5/3. Okay, so we have the base and exponent by itself. Now we switch to log form. Log base 1 plus 0.025 divided by 52 of 5/3 equals 52t. And now undo the multiplication of 52, divide by 52. So this is what we're keying into the calculator. Here's my fraction bar. Out the window number 5. Again, it's very important that you are keying this into your own calculator and not just watching me key into my calculator. So 20 points, and we're rounding to nearest tenth of a year. 20.4 years. If $100 is invested at 8% interest compounded monthly, after how many years will the amount in the account double? Okay, so $100 our starting amount. That's P. 8%, 0.08 is R. Compounded monthly, N is 12. And we're looking for the account to double. So 2 times 100 is 200 is our ending amount, A. So 200 is equal to 100 times 1 plus 0.08 divided by 12 raised to the 12t. Again, our base is here, an exponent, so first thing we want to do is divide by 100, both sides, and 2 is equal to 1 plus 0.08 divided by 12 raised to 12t. Now we switch to log form. This is our base, this is our exponent, and that's our answer. So log base 1 plus 0.08 divided by 12 of 2 is equal to 12t. And divide by 12. So into the calculator we are keying t equals log base 1 plus 0.08 divided by 12 of 2, all divided by 12. Definitely use the fraction key on the calculator. .6931 to the nearest tenth of a year, 8.7. The rate in exercise number 1 was referred to as nominal in name only. It's known as this because you effectively earn more than this rate if the compounding period is more than once per year. Because of this, bankers refer to the effective rate, or the rate you would receive if compounded just once per year. An investment with a nominal rate of 5% is compounded at different frequencies. Give the effective yearly rate accurate to 2 decimal places for each of the following compounding frequencies. So for quarterly, so we're only focusing on 1 plus r divided by n raised to the nt. I'm only focusing on this piece of our compound interest formula. So for quarterly, n equals 4. We'll take our 1 plus 0.05 divided by 4 raised to the 4 times 1. 1.05094. And if we, as we did in a few lessons earlier, if we subtract, or back in Unit 3, if we subtract the 1 and then multiply by 100, the effective yearly rate is 5.09%. If it's compounded monthly and is 12, grab that, change my 4s to 12. Subtract 1 times 500, 5.12%, and if it's compounded daily. .13%. And our third page, now we're looking at compound interest. We could compound at smaller and smaller frequency intervals, eventually compounding all moments of time. This gives rise to continuous compounding and the use of the natural base E in continuous compounding interest formulas. For an initial principal, capital P, compounded continuously, I say continuously has the E. At a nominal yearly rate, lowercase r, the investment would be worth an amount, capital A, given by the formula capital A equals P times E to the RT. Another formula to memorize. So let's write it off to the side. A equals P times E to the RT. So RT is the exponent on base E. This is your base and exponent here. Exercise 6, Tom invests $350 in a bank account that pays 2% annual interest compounded continuously. So as soon as you see that, you're using A equals PE to the RT. So 350 is our P, R is 0.02. Write an equation for the amount this investment would be worth after T years. Let's write our formula. A equals P times E to the RT. Capital A equals 350 E to the 0.02T. There's our formula. How much would the investment be worth after 20 years? We substitute 20 in for T. Go to the calculator. 350 E to a power, remember, would be, so just E itself is second division. E to a power is second ln. There's ln. E to a power is second ln. times 20. So it would be worth $522.14. Algebraically determine the time it will take for the investment to reach $400. Okay. 400 is equal to 350 e to the 0.02t. We want to get t is our variable we're solving for as part of an exponent. So we want to get our base and exponent by itself. So we have 350 times, undo the division, undo the multiplication by dividing, and 400 divided by 350, I'll math rack that, 8/7. Switch colors. 8/7 is equal to e to the 0.02t. Now we switch to log form. Remember, let's see, this is our base, that's our exponent, this is our answer. Log form, we spell out log base. So log base e of 8/7 equals 0.02t. Sorry, there's not much room here. Get t by itself. Divide by 0.02. And this is what's keyed into the calculator. Alpha y equals to get my fraction. Now, log base e is the same as ln, right? Log base e is the same as ln. So ln of 8 divided by 7 divided by 0.02. So 6 point, rounding to the nearest tenth of a year, 6.7 years. What is the effective annual rate for this investment, round to the nearest hundredth of a percent? All right, so in other words, it's simply asking us to, if we have e raised to 0.02 times 1, what is that equivalent to? Second ln e to the 0.02, and we will subtract 1 and times by 100 and get the percent. So 2.02%. Again, it's so important that you have your calculator and you are keying in everything into your own calculator as I'm doing into mine. You're not just watching me. If you're just watching me, you're going to have a hard time on any test or quiz or the classwork tomorrow and the next day. All right, exercise 7, you invest $2,500 in the account to save for college. The account 1 pays 6% annual interest compounded quarterly, and account 2 pays, all right, so we have two different investments. We have one investment that pays 6% compounded quarterly, so this is using, let's say this is account 1. Uses a equals p times 1 plus r divided by n raised to the nt, and then account 2 has 4%, pays 4% annual interest compounded continuously. So this uses a equals p times e to the rt. Which account should you choose to obtain the greater amount in 10 years? Justify your answer, so we'll be justifying it with our calculation. 2,500. is 4%. It would be account A. That's yields the greater amount. Or account 1, sorry. The above formula can be applied to any situation that grows at a continuous rate. Exercise number 8, a population of 314 seals on a tropical island is growing continuously at a rate of 1.5% per year. Write a function to model the number of seals on the island after T years. Okay, so it's growing continuously. So instead of having a principal, a dollar amount, we have a population amount of 314. So we're using A equals P times E to the RT. Right here, P is our population of 314. 0.015 to the T. So there's our function. And now algebraically determine the number of years for the population to reach 455. So 455 replaces our capital A. A variable is part of an exponent, so we want to get that base and exponent by itself. I'm just going to leave that. Now we'll switch to log form. Let's see if that fraction reduces. It does not. Switching to log form, log base E of 455 divided by 14 equals 0.015t, and divide by 0.015. So into the calculator, alpha y equals log base E is the same as ln. ln, I'm just going to go up and grab that, close that parenthesis, arrow down to the denominator, 0.015. Nearest tenth of a year, 24.7 years. Thank you very much for your attention. I apologize for the length.